Not all of my regions are going to be those that can conveniently be matched to a rectangular area. Now we need to explore general regions of integration. In order to get started, we need to use the ideas we have already with respect to computing double integrals and make them a little bit more useful when my region is not going to be rectangular. Rectangular boxes will never perfectly fill a region that has curved boundaries. I can certainly reduce the size of my boxes and make them smaller and smaller until they minimize the amount of error between the actual area of my region and the approximation of the region given by my Riemann sum. But the goal is still to take that limit of the Riemann sum to get a double integral over the region, just like we saw before. But I need to be extremely diligent about understanding a couple of key things that limit this approach just a little bit. The first is that in my non-rectangular regions, the order of integration is going to be critical. And the second is that we need to make sure that we know which type of region we're dealing with. There are two general types of regions that I need to consider. The first type are regions that are bounded from above and below by two continuous functions of the form y is equal to h of x and y is equal to g of x. This may include a region in which my h of x and g of x intersect at the beginning and the end of the interval I'm interested in. Or it could be that the two functions intersect at only one end of my interval, or the two functions may not intersect at either end of the interval. The second type of region that we're dealing with are regions that are bounded to the left and right by two continuous functions of the form x is equal to h of y and x is equal to g of y. Again, there are three basic types of curves to look for here. I may have two curves that intersect at both endpoints on my interval. I may have two curves that intersect at only one of my endpoints on my interval. And I may have two curves that don't intersect at either endpoint or in the middle of my interval. So I want to talk a little bit about regions versus volumes here. I want to keep in mind that the regions we're talking about are regions that describe a cross-sectional area of the solid. These regions can be thought of like a shadow that's being cast by a light that shines directly on my solid and projects the shadow down onto a plane below the solid or to one side of the solid. The equations that describe the boundaries of the region give us our limits of integration with respect to x and y. The functions that appear in my integrand describe the shape of the top and or bottom surfaces of my solid, or the left and or right surfaces depending on which type of region we have. These functions provide the height dimension of my 3D solid. So double integrals over non-rectangular regions can be described by letting a region R be bounded below and above by the continuous functions y is equal to g of x and y is equal to h of x, respectively, and the lines x is equal to a and x is equal to b. If f is continuous on this region R, then the double integral over the region R of f of xy dA is given by the integral from a to b of the integral from g of x to h of x of f of xy times dy dx. Notice that in this case, I'm first integrating with respect to y, and my limits of integration are my function values, g of x and h of x. If my R is a region bounded on the left and right by the graphs of continuous functions x is equal to g of y and x is equal to h of y respectively, and the lines y is equal to c and y is equal to d, if f is continuous on my region R, then the double integral over the region R of f of x y dA is given by the integral from c to d of the integral from g of y to h of y of f of x y dx dy. Notice that in this case, my inner integral is with respect to dx, and those limits of integration are the function values g of y to h of y. Fubini's theorem tells me that the integral from a to b of the integral from g of x to h of x of f of xy dy dx is not equal to the integral from g of x to h of x of the integral from a to b of f of xy dx dy. In other words, on my general region, the interchange of my integrals with the respective variables of integration are not generally equal. So let's look at an example. I want to evaluate the integral as written. This is a double integral. I have the integral from 0 to the natural log of 2 of the integral from e to the x to 2 of dy dx. I first want to graph my area region, my cross-sectional area. This is a graph in quadrant 1 between x equals 0 and x equal the natural log of 2 of the area bounded on the bottom by the curve e to the x and on the top by y is equal to 2. My inner integral is y evaluated from e to the x to 2. I plug that into my outer integral and I get the integral from 0 to the natural log of 2 of y evaluated between e to the x and 2 dx. This becomes the integral from 0 to the natural log of 2 of the quantity 2 minus e to the x dx. This gives me 2x minus e to the x evaluated from 0 to the natural log of 2. I get 2 times the natural log of 2 minus 2 minus 0 minus 1. This simplifies to 2 natural log of 2 minus 1. Now I want to work another example. I want to evaluate the double integral over the region R of the sum of x and y dA, where R is the region in the first quadrant, bounded by the lines x is equal to 0, y is equal to x squared, and y is equal to 8 minus x squared. I start by plotting my cross-sectional area for my region. This is an area in the first quadrant bounded by a downward opening parabola that has a vertex at 0, 8 and an upward opening parabola with a vertex at 0, 0. In the first quadrant, my two parabolas intersect at the point 2, 4. This gives me some limits of integration. My double integral over the region R of f of xy dA is equal to the integral from a to b of the integral from g of x to h of x of f of xy dy dx. For my region, this gives me the integral from 0 to 2 of the integral from x squared to 8 minus x squared of x plus y dy dx. My inner integral becomes xy plus y squared over 2 evaluated from x squared to 8 minus x squared. This gives me an integral from 0 to 2 of the quantity xy plus y squared over 2 evaluated from x squared to 8 minus x squared dx. My outer integral simplifies to become the integral from 0 to 2 of the quantity 32 plus 8x minus 8x squared minus 2x cubed dx. The integration gives me 32x plus 4x squared minus 8/3 x cubed minus x to the 4th over 2 evaluated from 0 to 2. This becomes 152 over 3. I want to work another example. I want to sketch the region of integration and evaluate the given integral as written. I have the integral from 0 to 4 of the integral from y to 2y of xy dx dy. Notice that I'm integrating with respect to x first. I want to sketch my region. My region is the region in the first quadrant that's bounded on the top by the line g of y is equal to 2y, and on the bottom by h of y is equal to y. It is also bounded by the line y is equal to 4. This gives me the integral from 0 to 4 of x squared y over 2 evaluated from y to 2y dy. This becomes the integral from 0 to 4 of 3y cubed over 2 dy. I get 3y to the 4th over 8 evaluated from 0 to 4, or 96. Now you get to try it. Pause the video and sketch the region of integration and then evaluate the given integral. When you are ready, restart the video to check your understanding. I want to evaluate the double integral over the region R of e raised to the sine y power dA, where R is the region in the first quadrant, bounded by the lines x equals 0, x equal cosine y, and the line y is equal to pi halves. The first thing I want to do here is sketch my cross-sectional region that I'm going to be integrating with respect to. And I get the region in quadrant 1 bounded by the x-axis on the bottom, the y-axis to the left, and the portion of the cosine curve on the right that intersects both of those axes. It intersects the y-axis at 0 pi halves, and it intersects the x-axis at 1, 0. Notice that the line y is equal to pi halves doesn't really matter for my region here. This tells me that my limits of integration go from 0 to pi halves in y and from 0 to cosine y in x, so that my integral from 0 to pi halves of the integral of 0 to cosine y of e to the sine y dx dy is the integral I'm going to evaluate. This gives me the integral from 0 to pi halves of the quantity x times e to the sine y evaluated from 0 to cosine y dy. This gives me the integral from 0 to pi halves of cosine y e to the sine y dy. I'm going to make a substitution. I'm going to let u be sine y so that du is cosine y dy. U of 0 is 0 and u of pi halves gives me 1. This changes my limits of integration. I get the integral from 0 to 1 of e to the u du, which is equal to e minus 1 as my final result. This is how I compute the result for double integrals over general regions. Be sure and let me know if you have any questions.